share and full screen. You can listen, you can hear me, yeah?
Yeah. Yes.
Good. So, I am Andrei Lebedь from University of Arizona, and today I will be talking about breakdown of the Einstein equivalence principle for a quantum body. So I must say that this is the most ancient question, the equivalence or non-equivalence on weight and energy. Of course, this is a joke, but this monkey, it weighs pineapple and say, what a heavy pineapple. I guess that it contains a lot of energy. Shall I discuss this issue with physicists? And my answer to this question is sometimes yes. So I must say that the equivalence of energy of inertial mass and gravitational mass for ordinary matter is established very well. And this is results from recent microscope space mission where they observed the acceleration of two cylinders, one with respect other, during 2 years and 5 months. And they found that this acceleration is negligible and estimated the accuracy that inertial mass minus gravitational mass over inertial mass less than 10 to minus 17, at least 16. There will be probably 2 other missions, Galileo Galilei. Microscope missions was French agency, Galileo Galilei Italian agency, and STEP satellite test for equivalence principle by Stanford University and NASA, which can give you 10 to minus 19 here. So this is the most established principle, but for ordinary matter. And first we consider ordinary matter, and we consider even classical case. So in classical case, I would say that the concept of gravitational mass of composite body is not trivial, because gravitational field is coupled not directly to the energy. This is kinetic energy and this is potential energy of the body, but it is coupled also to some term which is called virial term. But fortunately, in classical physics, there is a virial theorem, and if you take time average of this gravitational mass, it will still give you the Einstein equation, contribution from the potential and kinetic energy of electron is E over c squared. So this is the result of Nordtvedt and Karolib, and valid only in classical physics. So we start from Schwarzschild solution. This is, but what we need, it is not isotropic one. We need to make it isotropic, and this is called isotropic Schwarzschild solution for interval. And now we keep only phi to the first power. This is the so-called weak field approximation, and we do this weak field approximation. So first of all, we would like to reproduce the classical result. So this is action in gravitational field. This is the weak field approximation. And if you calculate contribution to Lagrangian function from kinetic energy, you will get this free kinetic energy term. So please switch off your microphones. I have some sounds. So this is three kinetic energy terms. So if you consider electromagnetic field just potential energy, Coulomb potential energy in the atom, you can calculate it in the standard way, where F is a Maxwell tensor of electromagnetic field. We have just electric field. So you will get that potential energy is now coupled to gravitational field as two potential energy over c squared. So this is very unpleasant situation. I also would like to tell you that we use no tidal effects approximation. So what does this mean? This means that the size of atom is very small, comparable to the radius of Earth, and we don't differentiate this with respect to electron coordinates. We don't differentiate the potential. So this gives you accuracy 10 to minus 17 power. So we don't need this. So how to get this Lagrangian in more natural way? You have proper local coordinate where you have interval in the Minkowski form, and you put here everything in standard Lagrangian in this local proper coordinate, and we will get Lagrangian in unperturbed coordinate, in inertial coordinate system, and this is famous term, three kinetic energy plus two potential energy. Potential energy is negative. So we can construct Hamiltonian, and we can reproduce Nordfeld and Karolyi results that indeed, if you average everything with respect to time, you will get the energy here and the virial term, which is zero. So this equation is valid only averaged over time in classical physics. So now what quantum physics introduced new in this area? So first of all, we can ask the following. We have ordinary matter. Each atom in the ground state, or it is better say in stationary state, it may be here. And we are asking about the mass of big object. So we should take average value of mass, or as we say in quantum mechanics, expectation value. So we quantize Hamiltonian. This is now weight quantization. This is mass operator times phi weight. And fortunately, in quantum mechanics, situation in this case is even better, because if you take not time average, but you take average of the via ensemble, through the ensemble, you have energy here and virial term, and average of virial term is zero. So we have for big objects that mass is represented by Einstein equation. But now we can ask two questions. First question is what we have for one measurements, because this is for big object. We took averaged value. What we have for one measurements, and second, what we have for more complicated ensembles. I call them gravitational demon, which is the superposition, coherent superposition of electron state. First question, we have this case, simple case, stationary case, but we have measurements now. So I don't have enough time to do this. So we have now quantum atom, and we switch on gravitational field. Virial term doesn't commute with Hamiltonian in the absence of gravitational field. Therefore, instead of simple Einstein equation, we will obtain a lot of opportunities what measurements give. Measurements give now quantized value of mass. This is n quantized number, and this is En, energy levels of hydrogen in hydrogen atom of electron energy levels. So instead of this simple equation, we obtain quantization. This is interesting. And this is published in these two reviews. So what is the probability? Probability is really small. Probability can be estimated as 10 to minus 18 for hydrogen atoms, but you know that Avogadro number is large. And Avogadro's number is 6 to 10 to 23 power. So it cancels this smallness, and we may have enough atoms which are in upper level states and which give you photons after the decay of this state. But the most interesting thing is if Einstein equation can be broken for average, for big ensembles. This can be really measured. And I found that can. Now we have the so-called gravitational demon. So we have superpositions of states, ground state and say first excited state. And we have ensemble of such coherent superpositions can be created by lasers. And the alpha here, the difference in phases between this and this function is constant. So we have superposition of macroscopic ensemble of superposition of coherent states. And this can be calculated using the standard two-level system and perturbation theory in quantum mechanics. But pay attention, now in perturbation, in addition to energy, we have virial terms. So we have virial contributions. So this is virial matrix elements for the non-diagonal elements of our equations. And if you calculate everything carefully, you will get that the average mass of such demon, of such gravitational demon, is not just bare mass of electron plus energy, and this is average value of energy over 2, but it contains also non-trivial term, but with cosine alpha. So if you have non-coherent matter, then this cosine alpha oscillates very quickly, and we will get Einstein equation. But if you coherent matter, which can be created, for example, by lasers in the case of ultra cold atoms, you have some contribution, And this contribution, you see, it is not small. So this is contribution from energy, but virial term is of the order of energy. And cosine alpha should be the same for ensemble, for the macroscopic ensemble. And we can calculate, we can contribute very large, and we can in principle measure this. At the moment, I'm not ready to discuss real experiment. I must say that probably we need lasers, not probably, definitely. We need lasers, and probably we need the matter, ultra cold matter. So this is just summary. So we establish Einstein equation for ordinary matter, but for ordinary matter, there is a small probability that individual quantum measurements give you different result. But for non-ordinary matter, for gravitational demons, and this is in contrary to Maxwell demons. You know that it is impossible to get Maxwell demons which break the second law of thermodynamics, but I found that it is possible to get gravitational demons. The equation, Einstein equation, is broken. So I did 17 times talk. I have 3 minutes for questions. So please ask questions.
Hi, I would like to ask a question.
Yeah.
I was wondering, this equation that you obtained for the energy corresponding to this system with 2 energy levels, how come the weight of the 2 energy levels is 1/2 for each one?
Yeah, I said that we have microscopic ensemble. So we calculate just average value or expectation value of energy and expectation value of mass, and they are not equivalent for big ensemble.
But the weight of the excited level should be smaller than the weight of the ground level.
Yeah, yeah. But we have combination, we have superposition. Therefore, E1 plus E2, this is the expectation value of superposition. And we have very simple superposition where the probability to be at level number 1 is equal to probability to be in level number 2. So we have small, and we don't have temperature equal to 0. So this is created by lasers.
Ah, yes. Okay, thank you. Thank you, I understand.
You're welcome. Yeah, you're welcome. So more questions? Okay. Amar, Galegas, are you ready?
Yes.
So you will have a talk. This is Amar Galegas from Ginvestav IPN. I don't know what it is. And University Paul Sabatier, one collaboration is University of Paul Sabatier. Yeah? And you have a talk, hydrodynamic representation for fermions in curved space-time. Please start.
I speak about the hydrodynamic representation for fermions in curved spacetimes.
You can make full screen.
Yes, it's in full screen. Can you see the full screen?
Okay, okay.
For fermion systems, there are some places in the universe where the curvature of the spacetimes is relevant. For example, in near to the black hole or a star or in the early universe. And for this reason, we consider the curvature, the systems in a curvature of spacetimes, the curvature spacetimes. There are some words where the hydrodynamic representation is worked. For example, here in this paper, the authors to find the energy balance equation for the boson particles, and the key is the hydrodynamic representation. Also, the Dr. Tonatiuh Matos and Dr. Chavani worked with me or developed this work for fermion particles. I present the field equation and what is the hydrodynamic description that we use for this work. And in this work, we use the tetrad and the tetrad and ADM formalism. We can write the metric in ADM decomposition like this, where the n is the lapse function and the ni is the shift vector. And in tetrad formalisms, we can write the metric in this form, where these are the tetrad coefficients. And the tetrad coefficients are related with the one forms and vectors. They are orthonormal themselves. Another important, or the most important thing is the action that describe the dynamical of the fermions.
I don't see that your slide are moving.
Can you see it now?
I see first slide.
The first slide only.
Yeah, now second, yeah.
Well, and in this case, I present the action that with we obtain the Dirac equation in curved spacetimes coupling with the electromagnetic field, where the C is the spinor and C Dagger is the transpose conjugate, and the mu is related with the covariant derivative and the potential vector in this form. And if we do the infinitesimal variation with respect to the adjoint spinor, we obtain the Dirac equation in curved spacetimes coupled with the electromagnetic field, and the gamma matrices are related with the geometry and the spin in this linear combination. And we can do the decomposition in ADM formalisms like this. And the gamma matrices follow the decommutation relation in this form, where the G mu nu is the metric that describes the geometry such as in general relativity. And another important relation is the Hermitian relation given by this equation. We note that if we take the B matrix equal to zero gamma matrix in flat spacetimes, we return to the standard quantum field theory definition. And if we do the infinitesimal variation with respect to the spinor, we obtain the transpose conjugate Dirac equation given by equation 9. And we define the adjoint spinor like this. This is equivalent to the standard quantum field theory, because if we take B matrix equal to zero component of the gamma matrices in flat spacetime, we return to the well-known definition in quantum field theory. And one important fact is that the covariant derivative of the gamma matrices in curved spacetimes, this relation is not zero. This is because the covariant derivative of the tetrad coefficients is not zero. And the density current for fermions is given by the equation 10. And again, we return to the standard quantum field theory definition if we take the B equal to zero gamma matrix in flat spacetime. The equation 11 is the continuity equation. This covariant derivative of the density current is equal 0 because we don't want to the spontaneous creation or annihilation particles. And with this fact, we obtain the equation 12. And the transpose conjugate Dirac equation is in equation 14. And these equations are the equation of motion of our system. We introduce the hydrodynamic representation for Dirac fermions. This hydrodynamic representation is given by the generalized Madelung transformation, because the Madelung transformation was introduced in quantum mechanics to do the hydrodynamic representation for Schrödinger equation, and again for the Klein-Gordon equation. And we introduced this generalized Madelung transformation in our spinor like this. This is each component of the spinor give half this form. More explicitly is given for this expression. We know that the R and theta components are different for each component in general. And these components are real scalars. And we know that the indexes with dot are internal indexes. And in the next slices, it's more convenient to take the R components with this square and N components, because the N have a physical interpretation for the number density. We can relate it for the electron-like spinor with the SO13 group, but this idea can be straightforwardly extended for more general groups. If we take this Madelung transformation in Dirac equation or in the continuity equation, we can obtain these relations. And if we take for each component of the spinor, we can obtain the equation 21. And if we do the transformation to the R to N vector, we can obtain this equation. The equation 22 is the Dirac equation, and equation 23 is the conjugate transpose Dirac equation. But it's more convenient for physical interpretation introduce these new definitions for density velocity is defined by this equation, and the S that is a phase by this transformation. And we can transform the Dirac and its conjugate transpose one like this with these new variables. And if we apply this operator in the Dirac equation, we can obtain equation 28. In this equation, we can observe that the first line is the Klein-Gordon equation, but in this case is for the spinor, and two extra terms. This is related by the electromagnetic interaction. And in this case, the last term is the most important for our description, because we don't obtain this term if we consider a flat spacetime or if we consider a system without a spin. If we introduce the new variables in the last equation, we can obtain this this equation, and this equation is the hydrodynamic representation for the Dirac equation. And another form to do the description, the fermions, is the Weyl representation. These two representations, Dirac and Weyl, can be related by the Lie groups, because in Dirac representation, we can relate it to the SO13 symmetry group, and in Weyl representation we can relate with the SU2. In this new representation, we can write every equation in Dirac equation like this, in this form. For example, the gamma matrices are written in Weyl representation like this, and the spinor in Dirac equation, in Dirac representation, is a spinor with 4 components, and in Weyl representation we can write in with 2 spinors with 2 components, the right and left-handed spinors. The same way is for the adjoint spinor. The gamma matrices is written in this form, and the density current can be written in this new representation like this, and more explicitly for the temporal and the space components in this way. And the gamma matrices can be written with when this new, more convenient form with the S matrices. The S matrices are the generally said Pauli matrices. What in that is the S matrix in this form, and this are related with the Pauli matrices in flat space-time. And with this new representation, we can write the Weyl equations. The Weyl equations are given in 42, and the other terms that appear in the Dirac representation can be transformed in this new representation like this, in these forms, and there are more convenient written in this form for the hydrodynamic representation that is in this. The Weyl representation is analogous like in Schrödinger and in Klein-Gordon and in Dirac equations by Madeleine transformation. The difference here is that the theta is our 2x2 matrix instead of in Dirac representation is a scalar, and R is a spinor of 2 components, and with this representation we can write the adjoint spinor like this. The 49th equation is the Weyl equations with this Madeleine transformation, and we can transform with the Madeleine transformation the density current, and we note that the 0 component of the density current is associated with the total number of particles with this M, and we can transform with this Madeleine transformation in the Weyl equations. We can obtain the hydrodynamic representation for Weyl fermions, and if we arrive for more convenient the terms, we can see in the first line, this is the hydrodynamic representation, and the next lines is the energy balance. I present the more specific what is each term. For example, here we can relate it with the kinetic energy, and we can write in better form like this. the first line is the hydrodynamic representation, and the second is the energy balance. And the energy balance say us what is the contribution of the energy in our system, the kinetic energy, the lapse potential, and the quantum potential, and what is the electromagnetic interaction, and this term, the last term, is the most the difference with respect to the boson particles or in a classical particles, because this term disappear if we consider a space-time, flat space-time, or a system with particles without spin. With this, one of the conclusion is that we find the first integral Bernoulli equation when we use the Madelung transformation in Dirac equation, and we can relate the two groups of symmetry for Weyl and Dirac fermions. And one difference with respect to the boson particles, the description, the hydrodynamic description for boson particles, that is that in the boson particles, the equations can be separated in imaginary and real part, but in fermion particles we
have 3 minutes.
Yes, we don't want this separation. And the important term is that the term that relate the spin and geometry. This is because we consider a curved space-time. And with this work, we can compare what the hydrodynamic description for boson and classical particles and fermion particles in the different regions of the universe. And we can study what is the hydrodynamic dynamical of these fermions and the different geometries. And that's it.
We need the time for question. Yeah.
That is all. Thank you.
Thank you. Please ask questions. I have a simple question. Why is hydrodynamical representation of Dirac equation is important? Where is it used?
Where? The hydrodynamic representation of the Dirac or for fermions in general is important because we can write, or we can do a description, the dynamical description of the fermion system in the different regions of the universe in the hydrodynamic representation. And we can compare with another hydrodynamic representation for boson or classical particles.
Okay, okay. So you now can switch.
Can I ask a question, please?
Yes, please.
Yes.
Please.
I'm a bit confused about this matrix B. So you mentioned at some point in the beginning that the gamma matrices are not conserved, don't satisfy nabla mu gamma mu equals 0 on a curved space. But did you take into account also the spin connection in computing this covariant derivative of the gamma matrices? Because the spin connection should be there to do exactly this, to allow the gamma matrices to be constant.
Yes, in general, the B matrix is given by what is the representation of the gamma matrices we adopt, what is the geometry that we work, and it depends of what description for spin or geometry we consider, because we take another representation for the gamma matrices and we have another B matrix. And I don't know if I asked your question.
I was just wondering on the covariant derivative for the gamma matrix. What is the expression? What formula did you use to compute this covariant derivative?
Yes. The gamma matrix in general is related by the tetrad coefficients and the another gamma matrices. We take the gamma matrices in flat spacetime that we well know. In this case, this is the relation that the gamma matrix, in generalized gamma matrices with the gamma matrices in flat spacetimes with these tetrad coefficients, and the covariant derivative is in respect with the tetrad coefficients.
Sorry, we can go further. So you can discuss. Let me, by the way, switch, break out room so you can discuss. Oh, this is not what I meant. This is not what I meant. And
thank you.
Yeah. So I don't see Antonio Ferreira is here. Yeah, please start your contribution. It is extended David Schwinger subtraction scheme, heavy fields and decoupling, University of Valencia and IFIC. Antonio Ferreira, please.
You're muted. Unmute.
Yeah, please start. Yeah.
Yes,
You're on mute.
Can you hear me?
Can
you hear me now?
Yeah, I can.
Yeah. Do you see my first slide?
Yes.
Okay. And the pointer also?
Yes.
Okay, perfect. So thank you for the invitation, first of all. So in this talk, I will present you a collaboration I did with my supervisor, Jose Navarro Salas, involving a renormalization scheme based on the David-Schwinger expansion. This will be the first talk that we will present, and the second talk, which will include some more details, will be presented by Sergi Nadal afterwards. So I want to first explain a bit about renormalization and curved spacetime. Then I will present the extended David-Schwinger subtraction scheme, and then I will try to give some application about the coupling and the cosmological constant running. So we know that how to construct a quantum field theory in curved spacetime by just extending the flat Minkowski spacetime to a general curved spacetime, considering the equation of motion, for example, for a scalar field, and then stating the commutational relation. And then we can construct from this some observables. For example, the net stress energy momentum tensor and the vacuum expectation value of the stress energy momentum tensor, or for example, also the propagator. And we realize immediately that this kind of observables magnitudes usually are involved the ultraviolet divergences, and usually they take the form as I state here, where if we integrate in 4 dimensions, we get already the usual Minkowski divergences plus some divergences associated with the curved background. So we usually need a regularization and a renormalization scheme in order to overcome these infinities and obtain a finite result that then we can give some physical interpretation. In a briefly introduction, the renormalization takes just the divergent piece and subtract exactly the same divergences as this piece in order to get a final result. And from this, the last years, the last decade, there has been a lot of development in how to construct consistently these subtractions in order to get final results. And there have been several regularization schemes, and these different regularization schemes, they give different results to the subtractions. They have, of course, the same divergences in order to correctly subtract the divergences, but they can give different results. Usually they have some requirements we need to have, for example, the conservation of the renormalized stress energy tensor, the construction, they have to be constructed by locally and geometrically terms. And an important result is that, of course, all the matter fields, the quantum matter fields, they are renormalized in the action, in the initial action, by just considering the usual Einstein-Hilbert term plus some higher order terms. But the important thing is that these terms are finite and it is perfectly renormalizable. So if we want, for example, to compute the effective action of a scalar field, a massive scalar field, then we can use the approach by computing, relating the effective one loop effective contribution to the Feynman propagator. This can be done by some computations. And then we can use, in order to renormalize or regularize this term, we can use normal coordinates with just an expansion of around, let's say, a point in a short distance. And then we can get isolate the divergences of, for example, here, the Feynman propagator, and in connection with that, the divergences of the effective action. Then what we can do is to go to the Witte-Schwinger proper time expansion. It's just a change of variables. And then we can also isolate the divergences. And in the case of the Feynman propagator, the divergences are isolated in the first and also in the one I put there, plus the first coefficient R1, and then the second coefficient that goes from this expansion is already finite. So we have a method that isolates the divergences of the Feynman propagator. In the case of the effective action, it is the same, but we have an additional divergences. So the second coefficient will be also necessary to isolate the divergences, but the next leading term is already finite. So the basic idea is then that once we have isolated the divergences of the one loop effective action, we say, okay, our subtraction scheme prescription is just take the divergent piece and just subtract from this the three first terms of the Witte-Schwinger expansion, and then you get a finite term. So this was already stated a long time ago, and what we proposed is just to include an arbitrary parameter that you can input in the construction of the Witte-Schwinger expansion, and we have called it mu squared. We just introduce it in the exponential part of the proper time, the Witte-Schwinger expansion, and we have to also change the coefficients in order to be consistent with not creating more divergences already than we originally had. And the benefit of introducing this mu squared, this arbitrariness in the expansion of the Witte-Schwinger, is that we get the usual mu dependence that we have from flat spacetime, for example, that we get a dependence in the energy parameter. So equivalently, as we would do in flat spacetime, we have that the effective action, the total effective action, which give us the semi-classical equation, and therefore they give us the physical content. It has to be independent of this mu parameter, of course, because it's an unphysical parameter. And therefore, if we know that the renormalized Lagrangian that we have already renormalized has a dependence on mu, it means that all the coupling constants of the classical action will also have this mu dependence equivalently as we would do in, for example, QED. And then we can compute the beta function for all the coupling constants. Sergi Nadal will afterwards explain this a bit in more detail, but I will just focus on the cosmological constant. We get the result that the cosmological constant has a running that is compatible with the coupling. And what this means is that if we have a mass that is higher than some energy scale mu, then the beta function goes to 0, basically meaning that very massive particles will not contribute to the running of the couplings that we have at low energy. This is a similar thing that happened in QED. In QED, for example, if we want to compute the polarization, the vacuum polarization of the photon propagator, we get a correction to, for example, the Coulomb potential encoded in this piece. And we have here used minimal subtraction dimensional regularization, and the same happens here. We think that the Coulomb potential is a physical quantity, therefore it has to be independent of mu, and that means that if this piece, this integral here has a mu dependence, also the electric charge would have a mu dependence, and then we get also the beta function of the electric charge that I put here. And then you can use this, for example, this running to predict the behavior of QED at high energies and all these kind of things. But the important thing for me, respect to the decoupling, is that we know that this kind of regularization scheme is not compatible with decoupling, because you know that you see that the beta function here is independent of the mass. This means that if we would have a very high mass, it would contribute the same even if you are at a low energy. So we know that the scheme of minimal subtraction is not compatible with decoupling. And this is a standard result, and it is solved by just changing your regularization scheme and go to a what's called momentum subtraction scheme by just changing how you subtract the divergent pieces. And then you get the result that you wanted, that when the mass goes to infinity, where you have a really high mass, then both the beta function and also the quantum contribution goes to 0. And this means that this is compatible with the decoupling. This means that this scheme is compatible with the decoupling. So coming back to the curved spacetime with the cosmological constant, I have stated that our scheme, what we call the extended de Witte-Schwinger scheme, is compatible with the coupling because our beta function just has the same result. You go when m goes to infinity, the beta function goes to 0, which again means that very high mass don't contribute to the cosmological constant at low energies. The same happens here in equivalently to flat spacetime, which means that if you you can also regularize the effective action in curved spacetime by using minimal subtraction, but then you get a running that goes to the m to the 4th, the mass to the 4th, a logarithmic term also. And if you take, for example, the cutoff regularization, you get a contribution which is cut off to the 4th. But this is standard result, which, because I have already mentioned that we know that minimal subtraction, for example, is not consistent with the coupling, and you have the same problem here as you would have in QED. But the problem is here that because of the dimension of the cosmological constant, it goes energy to the 4th, and it's even a bigger problem, a really, really big problem, which is usually stated as one of the cosmological constant problems. So what I have stated is that if you go to the extended de Witte-Schwinger scheme, you have a running that is compatible with the coupling, and this means that you can construct consistently an effective field theory approach where you have your quantum contribution of a very massive field, but you want to compute the contribution at a low energy. And how you do that is you just take the effective action that you would have at a high energy, and then you use the de Witte-Schwinger expansion in all the other terms that I have not included because they are already finite. But you can use this expansion in order to construct an expansion that has inverse powers of mass, which is exactly what we want to have for an effective field theory of this high massive scalar field. And when you compute that, you get the standard results for effective field theory. One, that you have this inverse powers of contributions of mass contributions. And then you have only a shift in the couplings, and this shift is consistent again with the coupling if you use the standard David-Schwinger expansion, the standard David subtraction scheme, because the contribution between the constant of high energy and low energy is just a term that goes mu to the 6 divided by m2 squared, and for a very high massive field, this is negligible. For example, if you take the observed data for the cosmological constant and take, for example, the electron mass, you will see that the contribution of the electron mass is negligible at low energies. So to conclude, quantum field theory in curved spacetime has many difficulties, but one of the most important things that it has divergences in the magnitudes, and you have several regularization and normalization schemes that you can use. We have proposed a novel subtraction scheme, which has the advantage that it's compatible with decoupling. Since all the standard methods, which include minima subtraction or cutoff regularization, they are usually not compatible with decoupling, in particular to the cosmological constant. And this non-decoupling is behind most of the problems of the cosmological constant problem. And so the thing is that you can construct an effective field theory approach by just switching to a regularization scheme that is compatible with the coupling, as is the extended David-Schwinger subtraction scheme. And that's all. Thank you.
Thank you. Please ask questions. You mentioned about quasi-classical approximation. What is the quasi-classical parameter? What is bigger than something?
Sorry, can you repeat?
You mentioned about quasi-classical approximation. What is the quasi-classical parameter in your theory?
Quasi-classical
approximation? Something should be bigger than something.
Well, I mean, I have you have if you interpret the mu parameter as your energy scale, or a physical scale, let's say, for example, the curvature, or whatever physical scale the dominant physical scale you have, then you will say that the curvature is smaller than the mass of the field you are computing, for example, the electron mass, which is the smallest mass of the standard model. Well, you say that the curvature is smaller than this mass.
Okay, thank you.
Okay.
Yeah, if there are no questions, please ask. There is 3 minutes for short question. Okay, thank you.
Thank you.
The next is Victor Ambrus. Victor, are you here? Yeah, chiral vertical effect for free fermions and anti-de Sitter space, Goethe University.
Thank you. It's a great pleasure to talk at this conference. I will be presenting some results obtained in collaboration with Elizabeth Winstanley from the University of Sheffield in the UK. This is the outline of my talk. I will start with the introduction slide. Then I will talk a bit about rigid rotation in Minkowski. Then I will describe rotating finite temperature states. I will show you the rotating thermal propagator on anti-de Sitter that I will use, and then some applications for the chiral vortical effect, and then I will conclude. So vortical effects refer to the generation of currents along the vorticity in a fluid, and they have been known to be relevant for rotating black holes including frame dragging effect, neutron stars, where they can be associated with anomalous transport, or the quark-gluon plasma, where spin polarization was measured by the star collaboration. And why am I focusing on ADS in this work? Because anti-de Sitter is a relevant space-time to study, for example, the quark-gluon plasma or strongly coupled quantum field series through the ADS-CFT duality. And also, anti-de Sitter has a time-like boundary. So this is very useful because no speed of light surface forms, and therefore we end up with a causal system even when we have finite rotation. So this is a cartoon of the anti-de Sitter space-time. This is a Penrose diagram showing its conformal structure. So as probably everybody knows, anti-de Sitter is a maximally symmetric solution of the Einstein equations corresponding to a negative cosmological constant. I will use this parameterization here, where we have a temporal coordinate, a radial coordinate, and here are angular coordinates. And the radial coordinate and the temporal coordinate are in principle bounded. So the radial coordinate is bounded by pi/2. This L is related to the curvature of anti-de Sitter. And what's interesting from this conformal diagram here is that the boundary of ADS, in fact, can be reached in finite time by null geodesics. So light rays can reflect from the boundary of ADS and come back into the bulk of ADS in finite time. Also, the periodicity of the time coordinate means that we have closed time-like loops. So in order to avoid this pathology, I will work in the covering space of ADS, in which this conformal diagram here is unwrapped. So this identification here will no longer apply. What does it mean to have a rigidly rotating state? Let's go to space-time which has central symmetry or exhibits spherical symmetry. So for such a space-time, the generic form of the line element is this one given in equation 1, where you have a prefactor W, and we have two more functions u and v corresponding to the radial coordinate and the unit length on the sphere. And on Minkowski space, we have that all these functions are equal to 1. On anti-de Sitter, using the parameterization that I showed before, we have some non-vanishing values for w and v. And what we can do from this metric is we can think about some macroscopic states that can live on this space-time. So one way to describe macroscopic states is to use something like the Boltzmann equation of kinetic theory, which has an advection part and the collision part. And the collision part is such that it draws the distribution function f towards some local thermal equilibrium. This is f equilibrium here, and f equilibrium in principle is a function just of this combination. Sorry, this is p or k. This should be the particle momentum. So trying to find now global thermal equilibrium states, we should throw this function in the Boltzmann equation. And it's a known result that in global thermodynamic equilibrium, this parameter beta, which is the temperature, the inverse temperature for vector, should satisfy the Killing equation. So beta is parallel to the velocity, macroscopic velocity of the fluid, of the state, and here is the inverse temperature. Now, if we want to describe a rigidly rotating state, we will find that rigid rotation is a solution of the Killing equation, where beta takes this simple form. So again, I'm using the coordinates shown in equation 1. Omega is the rotation parameter, and beta 0 is the value of the inverse temperature on the rotation axis. So the velocity can be extracted from this beta, and we have here a Lorentz factor gamma, which basically takes into account the velocity that a particle which is co-rotating will have as it moves away from the rotation axis. So this rho is some kind of an effective horizontal coordinate. What happens now is through the Tolman-Ehrenfest law, the temperature and the chemical potential will depend on position. So they are related to their value on the rotation axis by this Lorentz factor, gamma. So this is what rigid rotation looks like in Minkowski space. I represented here some Cartesian coordinates, and we consider a fluid which is undergoing rotation around the z-axis. So what we can identify here is a tetrad of kinematic vectors. We have first the velocity, which describes rigid motion. We have the vorticity itself, which is related to this direction along which we want to impose rigid rotation. Then we have a centripetal acceleration pointing towards the center. And we have a fourth vector, which is orthogonal to all these three vectors. And here is the T phi representation of this vector tau. So the velocity I just showed you before. The acceleration is just the covariant derivative of the velocity along the velocity, and it points radially towards the origin. The vorticity points along the vertical direction. And you can notice that there are some Lorentz factors here, which appear in all these quantities. So what's interesting on Minkowski space, if we study rotating states, is that one can find a finite value of the axial current, which is directed along the vorticity. And the coefficient appearing here is called the axial vortical conductivity. And its expression is given by this formula. And here I restricted this expression to vanishing chemical potentials. So there is a t-squared term here and some term which depends only on vorticity, acceleration, mass of the quantum. Let's now move to the anti-de Sitter space. So we have again those four vectors that I mentioned before, but now because of the curvature of anti-de Sitter, there are some modifications that I would like to show to you in this plot. So first of all, we have some effective vertical and horizontal coordinates. So here are lines which are of constant vertical coordinate, which end in this point here. This red circle is the boundary of anti-de Sitter, so it's r equals pi by 2 basically. And each slice of constant z will end on this point in the equator. And here are lines of constant horizontal coordinates. So you see that these curves bend. And now if we look at the vorticity will be tangent to these curves of constant rho. So they will point along the z direction, basically. And the acceleration has, in fact, two contributions. So there is one radial contribution, which is due to the nature of ADS. So ADS likes to clump stuff together. So you need some acceleration in order to escape from being pulled towards the center. And this acceleration plays the role of the centripetal acceleration that I showed you before. So it's the part that depends on omega. And now we ask the question, how does the axial vortical effect change when we introduce this curvature of ADS? And there is, again, the simple law that the axial current is proportional to the vorticity. And in the axial conductivity, one can find a correction, which is proportional to the Ricci scalar. So this is the punchline. Now I will show you some steps in the derivation. So how does one compute expectation values at finite temperature? I will use this point splitting approach, in which, first of all, I need a density of states operator, this curly rho, which is a Boltzmann factor, taking into account the Hamiltonian and the angular momentum operator for the system. So an expectation value of an operator A at finite temperature and finite rotation is the trace over Fock space of the product of this density of states operator and the operator itself. Using point splitting, one can obtain, for example, for the axial current, its expectation value by taking the coincidence limit and the trace over the spinor indices of the corresponding propagator for this state at finite temperature and rotation. So in order to find this propagator, this is going to be the topic of the next slide. It's useful to consider its decomposition along the causal structure. So we have here a step function, which is taken along the thermal contour. You see that in the thermal contour, we have this deviations towards imaginary times of the Weidmann functions with a plus and a minus. So in thermal systems, there is this so-called KMS relation, which allows one to relate the minus and plus Weidmann functions. And taking into account the fact that we are in the Heisenberg representation, the field itself obeys this simple equation, which can be regarded as some equation of motion. So when we put psi between rho and rho to the -1, the effect is that the temporal and the angular coordinates are shifted, because these operators H and MZ are the generators of translations in time and of rotation. And notice that we get an extra spin term here, which is related to the fact that we have to rotate the spinor structure as well. This spin term survives also in the KMS relation. And in the end, it's a term that we need in order to construct this thermal propagator as a sum over the vacuum propagators here. So you notice that still the spin term is here. Okay, so because on anti-de Sitter we don't have a spin of light surface, this propagator here at finite vorticity but vanishing temperature is in fact the vacuum propagator. Let's do some calculations now. We obtained the thermal propagator in terms of vacuum propagator. What does the vacuum propagator look like? Because anti-de Sitter has maximal symmetry, the vacuum propagator can be written in this simple form. So we have here two functions, which are scalar functions. We have here this so-called bi-spinor of parallel transport. And n slash is the contraction of the tangent to the geodesic to the gamma matrices. This S here is the geodesic interval between points x and x primed. It has a known expression of anti-de Sitter. And basically these two functions satisfy some coupled differential equations, which can be solved exactly. And here is the m equals 0 limit just to show you their expressions. So the bispinor of parallel transport, in fact, because anti-de Sitter has maximal symmetry, can be obtained by solving this equation here, which is basically guarantees that lambda performs parallel transport for spinors. And for a particular choice of Cartesian tetrad, it can be found in closed form. So here is the reference for those who would like to see the derivation. So it has a closed form expression which can be used in calculations. So now, if I want to compute the axial current, I will just throw everything that I showed you in the machinery and obtain this value for the axial conductivity. So it's a sum over J, which I showed you before, and it involves evaluating basically this geodesic interval on the thermal contour. So we need to shift the coordinates, x and x prime, in fact only x, along this thermal contour to imaginary values. This is the expression for any mass. So K here is the ratio between is the product between the mass and the length, the curvature length. Here's some hypergeometric function, and at large temperatures, one is able to derive this limit, which is the Minkowski expression plus the correction. Let me now show you some other results. So one peculiarity on anti-de Sitter is this competition between the clamping effect and the centrifugal effect. So we turn on rotation and basically we are throwing everything out towards the infinity. And this competition is in a perfect balance for so-called critical rotations. So here the rotation parameter times the curvature, the radius of curvature L, has the value 1. In this case, if we go to the equatorial plane, so where theta is equal to pi by 2, then we notice that the temperature actually will be constant. So we'll have the same value throughout this equatorial plane. And in particular, substituting this limit into the axial vortical conductivity, we end up with an expression which is independent of R. So this is for any mass. This is the temperature here, but there is no coordinate. Now I'll show you some numerical results. So computing this axial vortical conductivity by evaluating the sum exactly, numerically, this curves, which are shown with lines and symbols, are obtained. And this dashed line is the high temperature limit derived on the previous slide. So you can see that the agreement is relatively good. We have here large temperatures and 3 values of the rotation parameter. So these sit here at the top of this plot, and small temperatures. And in the small temperature regime, there is some discrepancy. One can see here, but it's very small. At omega bar equals 1, this is the critical rotation. We see that the axial vertical conductivity is constant everywhere. And because the temperature decreases basically with the radial distance when the rotation is not critical, we expect some deviations close to the boundary. When the mass is turned on, so K is again the mass times L, we see some more pronounced deviations to the analytical expression, which is to be expected since here the mass is comparable to the temperature. So the temperature is also equal to 2. Here is a log-log plot just for critical rotation to test again the validity of the asymptotic formula, and it works. So I will skip this, and now I would like to tell you a bit about the axial flux. So the chiral vortical effect is famous because it generates a current which is parallel to the vorticity. So this means that if we go to the equatorial plane, we will see some current of chirality which goes upwards everywhere on anti-de Sitter space. How can this happen? Because ADS is basically a closed manifold. We have some conservation equation here, which tells us that, in fact, the axial current is conserved if the mass is 0. If the mass is not 0, then we can have this conversion of axial flux into the pseudoscalar condensate. This is just the psi bar gamma 5 psi. So let's compute the flux of the axial current through slices of constant z bar. So these are the slices of constant z bar. Here is there are some volume integrals here that one needs to do, which can be performed. So the final expression is again some function, something involving hypergeometric functions, and there are 2 features here that I highlighted in color. One of them is notice that if omega goes to 1, then this denominator here blows up. So we can expect that the axial flux will be in fact infinite because the axial vertical conductivity stays constant in the equatorial plane. Therefore, in the equatorial plane, we expect to have the same axial current everywhere. And since there is an infinite area, that will generate an infinite flux. And here is another term which depends on this z bar, which tells us that there is a decrease in the axial flux.
You have 3 minutes.
Perfect, thank you. Decrease of the axial flux as we move towards infinity, but only if the quanta is massive. If the quanta is massless, then there is no decrease. So here is an asymptotic expression of this flux for large values of z bar. So as we approach the boundary of anti-de Sitter, here is the term that I mentioned. So it's a divergent term towards critical rotation. And here is how the axial flux drops with z bar. So a log-log plot here confirms that for massless particles, we have a constant axial flux, whereas for finite masses, we have this decrease. So what we can conclude from here is that for massless particles, in fact, the flux that we find in the equatorial plane must originate from the southern hemisphere, from the boundary of ADS, and must flow through the northern hemisphere, again, through the boundary of ADS. So ADS is transparent from this point of view to massless particles. Here is the large temperature limit. I will not discuss this in order to save some time for questions. And I will leave you here with my conclusions, and I welcome any questions you may have. Thank you.
Thank you very much. Yeah, now please ask questions. Probably you have a time to explain what is written on the previous transparency.
Yeah, sorry for skipping this transparency. So when one computes the high temperature limit, again, this divergent term can be identified, which is related to the critical rotation. And the behavior resembles in some sense that of the axial vertical conductivity, because the leading order term goes like t squared. So here is some comparison of this asymptotic formula here, which just validates these terms here. I see a raised hand.
Yeah, thank you very much.
If there is still time, I see Omar has the question.
Yeah, if anybody.
Can you do this analysis for another geometry or instead of the anti-de Sitter, or it's only for this geometry?
Yeah, in fact, this is a good question. So one could think of a setup in which to do this analysis in a more general way. The reason why I focused on anti-de Sitter is because of its maximal symmetry, which allows many of the calculations to be done analytically. Of course, if you go to a more general space-time, then you have to rely on some approximations and take either small curvature or a small rotation parameter. But yes, for sure, this is, as far as I know, has not been done yet. General formula for the vertical conductivity for any space-time. So this correction that I showed you here could well be just for maximal symmetry. Maybe there are other terms.
Okay, thank you very much. Thank you. So the next is Sergey Nadal. And this is renormalization running couplings and decoupling for the Yukawa model in space, in curved space-time.
Okay, can you hear me?
Yeah, University of Valencia.
Okay, thank you. So now I will be presenting the work that I have currently doing together with Antonio Ferreiro and Jose Navarro Salas, where we will compute the beta functions of the Yukawa model in curved space-time using the de Witte-Zwinger generalized method already presented by Antonio Ferreiro before. So the outline of the talk will be the following one. I will briefly review what Antonio already said by introducing what is decoupling, the de Witte-Zwinger subtractions, and how can these subtractions be generalized. And then we will show the results that we have obtained in the Yukawa interactions. Okay, so let's begin by saying that decoupling is a property that ensures that we can separate low energy physics from very high energy physics. There is a statement in flat spacetime done by Appelquist and Carazone, which says that very massive particles, much massive than the energy scale where we are doing our physics, should not contribute to any computed observable. For example, if we have the Fermi theory, we can compute nice results without knowing about the gauge bosons, while we keep in the regime where, in this case, the momentum, the physical scale, is much smaller than the gauge boson. So this gauge boson do not contribute to this Fermi theory, this effective field theory, with less degrees of freedoms. So therefore, the decoupling property has to be encoded in the beta functions of the theory, because the beta functions states how our parameters run with the physical energy scale. So in perturbative quantum field theory, as Antonio already showed, we can compute the beta functions by using the renormalization prescription, and this beta function will depend on the renormalization scheme. So for example, in dimensional regularization with minimal subtractions, we can compute the beta function for the electric charge of this vacuum polarization diagram. And we see that this beta function does not have the property of decoupling. So we have to move to a mass dependent or momentum dependent scheme where this beta function has the following form. And we see that when the mass of the fermion loop is much bigger than the mu scale, this goes to 0, thus ensuring the decoupling property. So what happens with quantum field theory in curved spacetime? Now, in curved spacetime, we will deal with a different approach where we study a classical background and we study quantum corrections to this classical background. We have to deal.
I cannot hear you.
Ah, sorry. Let me see. Maybe. Okay, can you hear me now?
Yes.
Okay. So I was saying that in curved spacetime we will deal with classical backgrounds, and we will study quantum correction to these backgrounds. And in this case, we have to deal with new methods of renormalization, because we have to deal with vacuum expectation values of the stress energy tensor, which contains ultraviolet divergences at the vacuum level and cannot be renormalized by normal ordering. So new methods are studied, like the De Witte-Svinger renormalization method, already presented by Antonio, which is it is very useful because it is general for any arbitrary spacetime. So let me explain a little bit how it works again. So for example, we consider the one loop effective action. We consider the Hilbert-Einstein action, and we study quantum corrections coming from the scalar field, non-minimally coupled to the scalar curvature. So we can compute the one loop effective action in equation 4, which is given by the Feynman-Green function, which obeys equation 5. So this equation has no analytic solution, but as Antonio already showed, it can be expanded in an adiabatic series, which allow us to control the divergences of the one loop correction. So these divergences are localized in the first terms of this expansion, which contains the following coefficients, which will produce modifications to the Hilbert-Einstein action. And we see in this block that the divergences are localized when the S parameter goes to 0 in the below limit. So for higher terms, this integral is already finite. So now we can compute the one loop correction by taking the analytic solution coming from the field, the equation of the field modes, and subtracting these adiabatic terms. So as Antonio said, this arbitrary parameter mu can be introduced, for example, in order to take into account an infrared divergence when the mass goes to 0. And this will produce the running of the parameters of our theory. The Debye coefficients have to be modified in the following way. And now we will see some examples where the Yukawa model, we compute the beta functions and see how decoupling appears. So let's consider first an easier example, which is where we have a gravitational background as well as an electromagnetic background. So we compute the one loop correction, which depends on this arbitrary mu parameter. And in order to require that the total effective Lagrange should be independent of this arbitrary mu parameter, the parameters of our theory, the constants, should run with this mu parameter. Okay. So by requiring this, we can compute the beta functions, and I will show now only the results. So for example, for the electric charge, we get the following beta function. And this very nice result of the beta function shows both regimes. The infrared regime, when the mass is much bigger than the mu parameter, and we obtain the decoupling property. So when m is much bigger than mu, this beta function goes to 0. And we recover also the ultraviolet regime stated by dimensional regularization with minimal subtraction, recovering the same beta function as minimal subtraction. This is very nice because we get both regimes, but moreover, we can get the running of the gravitational couplings. For example, here we have the cosmological constant and the Newton gravitational constant. So we see here again that we get decoupling when the mass is much bigger than mu. So, okay, is this stable for more interactions? And what happened with other dimensional parameters? We try to answer these questions by studying the Yukawa interactions, where in this first case, we will have a classical background, classical scalar background, and we will consider the scalar quantum corrections to this background. So we can compute the one loop effective action by taking the equation from the Feynman-Green function. And we see now that we need to include a new term, which is proportional to the scalar background. The Debye coefficients have to be modified to include the scalar background. And this will give us a new term required for renormalization. We can compute the beta function. And here I'm showing just one of the beta functions required for renormalization, the parameter required for renormalization. So for example, for the parameter of the non-minimally coupling to the scalar curvature, which is a representation of a representative of the dimensionless parameters, we observe that we get the expected ultraviolet regime when mu is much bigger than m, as well as the infrared regime when m is much bigger than mu, so getting the coupling property. For the other dimensional parameters, we also get the coupling, as we can see, when the mass of the scalar quantum field is much bigger than mu. So okay, again, we get the same beta functions for the cosmological constant and the gravitational Newton constant. So we see that the coupling naturally appears for all the parameters. Now we move to study the quantum corrections coming from a Dirac field coupled to this scalar classical background via the Yukawa interaction. So now in this case, in order to do the Vites-Binger expansion, we need to take the Klein-Gordon equation for the Dirac field. So in this case, the Q parameter obeys equation 10. I have highlighted here in blue the mass of the Dirac field, because usually in this expansion, we do not get a term proportional to the mass. And this will have consequences in the beta function of the mass of the scalar background, as we will see in the last slide. Okay, so I'm showing here some of the beta functions that we have obtained. So for example, for the dimensionless parameters, which is the z, the wave function of the scalar background, we get that the mass, we get that it obtains the same ultraviolet regime as it is obtained by dimensional regularization with minimal subtraction. And we get also decoupling when the mass is much bigger than the mu parameter. So this is very nice, because for all the dimensionless parameters, we are recovering the ultraviolet regime given by minimal subtraction, as well as the infrared regime expected with the decoupling property. We also get a running for the cosmological constant, as well as for the Newton gravitational constant. And we see that we get decoupling when the mass is much bigger than mu. However, for the mass of the scalar background, we have a term proportional to the m squared, which does not allow to get a full decoupling. So finally, I just want to conclude that we have checked that decoupling naturally appears for all the dimensionless parameters. We also recover the standard result in the ultraviolet regime given by minimal subtractions for all the dimensionless parameters. And we have also get a running of beta functions for the dimensional sector with the cosmological constant, gravitational Newton constant, and the mass of the scalar field, which obeys the coupling property expected in the infrared regime. In further work, we would like to properly understand why the Dirac correction does not give full decoupling for the mass of the scalar field, and analyze situations for the where we can get a proper where this work of the running of the parameters would be interesting. For example, the Higgs stability, preheating, and so on. And this is all I wanted to say. And if you have questions, please go on.
Thank you very much. Please ask questions. There are time for 2 questions. There is time for 2 questions, yeah.
Can I ask a question?
Yeah.
It seems like the beta functions that you obtained for the cosmological constant and for the Newton constant are more or less of the similar form for both the Dirac field and the Klein-Gordon field. So is it possible to perform a similar analysis where you include both bosonic and fermionic fields?
So you mean, well, I mean, those, yes, those beta functions would sum together because you are studying the quantum contribution from a Dirac field as well as the quantum contribution from a scalar field. Maybe you are asking that if we have some other interaction with the quantum Dirac field and the quantum scalar field, or
yeah, that was my next question. If you take into account that this scalar field, that the scalar field and the Dirac field are interacting.
Okay, so we have not done this, and yeah, it is. I don't know exactly how to do it because here we will have to study in more detail how to build this De Witte-Zwinger expansion where we have both quantum fields. So I'm not sure how to do it.
Thank you.
Okay, more questions. Then we can say thank you very much to Sergi.
Okay, thank you.
And now we proceed to the black hole induced false vacuum decay from the first principle. Andrei Shkerin, University of Minnesota.
Yeah, hello everyone. Can you please stop sharing the screen so I can share my screen?
Yeah, let's wait.
Yeah.
Can you share it now?
Yes, it's good. Can you see it?
I can see.
Yeah. Okay, thank you for the opportunity to give a talk. I will talk about the recent work done in collaboration with Sergei Siberyakov from Perimeter. Okay, let me start with some motivation. So why it is important to study false vacuum decay in field theory? Because it may have something to do with real-world fundamental physics. It is known that if you take the standard model Higgs potential and consider the quantum corrections to it, then at some high energy scale, the potential can become negative and a new vacuum, new minimum may appear here, which makes our electroweak vacuum where we live not absolutely stable. And now there is a possibility to tunnel from here to here. This topic is of considerable interest. Here's a very incomplete list of papers dedicated to it. And the general conclusion is that although in our present day universe, with its low temperature and low curvature background, the tunneling probability is sufficiently low, the situation can be different in different environments and in different epochs of the universe. The Higgs vacuum stability has been studied in many various setups, in the standard model and its modifications, in thermal spacetime with gravitational corrections taken into account, at finite temperature, and also in the presence of local space-time inhomogeneities, such as black holes. So let me explain why black holes are so interesting in this respect. The general expectation is that any impurity dropped into homogeneous background accelerates phase transition. So apparently black holes can do the same, but two things make them special. The first is that black hole is a quite simple example of space-time inhomogeneity. This makes the problem tractable, sometimes even analytically, especially in models of toy models of gravity in 2 dimensions. The second thing is that a black hole provides an example of non-trivial structure of quantum vacuum, which manifests itself as Hawking radiation. This means that to answer the question how black holes catalyze vacuum decay, one should understand not only how curved background geometry affects the decay rate, but also how a source of radiation affects it. And note that even if the source is thermal, the whole system is not in thermal equilibrium here because the particle flux is anisotropic. This problem is not new, but the interest has been revived recently because of its possible implications of phenomenology. What's the possible logic here? Black holes evaporate, and an evaporating black hole, it scans all possible temperatures, presumably up to the Planckian value. And at some point, vacuum fluctuations may become so strong that they just drive the system over the potential barrier separating the regions of false and true vacuum. And if true, this would put strong constraints on the models of primordial black holes in the early universe, because it would exclude a single light primordial black hole, no causal path. Or alternatively, it would imply that the Higgs potential behaves so that there is no instability in the electroweak vacuum. All this calls for a consistent and general framework to address the problem. So let me explain what our framework is. Let's be as simple as possible. So we go to 1 + 1 dimensions where things are simpler. We switch off completely back reaction of vacuum decay on background geometry. So the gravitational background is fixed. And we consider the simplest model of real scalar field with unstable potential. So the metric is given in this form. Omega is a conformal factor. We take the geometry to be asymptotically flat. And near horizon, at x going to -infinity, the factor behaves in this way. In fact, this is the Rindler metric, which approximates the near horizon geometry. These coordinates t and x, they span the physical wedge of the maximally extended black hole spacetime, and our vacuum boundary conditions are imposed here and here in the remote past, and x going to ±infinity. The parameter lambda here is related to the black hole temperature, and here's the action of the scalar field. The parameter g here is a small coupling constant that controls semiclassical expansion. And this is a schematic picture of the potential. The false vacuum is located at phi = 0, and we choose the true vacuum to be at phi going to +infinity, but this is not really important. One can as well choose it to be at some finite value of phi. Now, yeah, the most important thing here is that to understand that a false vacuum, like any vacuum state, it is characterized not only by expectation values of fields, but also by structure of fluctuations, quantum fluctuations around those values. And our method should be able to discriminate between various vacuum states that exist in a black hole background. So what are these vacuum states? They can be described using the standard decomposition of the real field in terms of left and right moving modes and associated creation and annihilation operators. So we consider 3 vacuum states. The Bulvar vacuum is defined as a state which is empty both of left and right modes. So there is no outgoing radiation and there is no radiation going into the black hole. Physically, this corresponds to an eternal black hole in empty space or a black hole mimicker. a hypothetical horizonless object almost as compact as black hole. Next, the Hartley-Hawking state is defined as a state in which both left and right modes are thermally populated. Physically, this is a state of a black hole. This is a situation of black hole in thermal equilibrium with the surrounding mass of particles. Finally, in the Unruh vacuum state, the right modes are thermally populated and the left modes are empty. So there is Hawking radiation, but there is nothing falling in. Physically, this is the most interesting case since it corresponds to a black hole that was once formed due to collapse of matter. We see that the Unruh vacuum is, in a way, it is in the middle between the Bulvar and Hartley-Hawking states. Roughly speaking, there are half as much excitations in it as in the Hartley-Hawking state. Since we believe that any excitation accelerates vacuum decay, even without any computation, one can guess that the vacuum decay rates are ordered in this way. So the probability is the biggest in the Hartley-Hawking state and smallest in the Bulvar state. It is important to know that in these two cases, there are in principle known prescriptions how to compute vacuum decay rate. But no such prescription is available for the Unruh state. So here we should really go back to the roots and develop it. So let me explain our approach. Very generally, we can take this vacuum transition amplitude from I to F, where I is some initial state close to the false vacuum state, and F is a final state, which belongs to the basin of attraction of the true vacuum. And for the decay probability, we can simply write this expression. We square the amplitude and we sum over all appropriate final states of the system. We can write this transition amplitude using the path integral. So we simply project onto eigenstates of the field operator. And the evolution here runs from some initial moment of time to some final moment of time along this part of the contour in the complex time plane. When we take the conjugate amplitude, this gives us another part of the contour, which now runs from Tf to Ti. And we may think of this expression for the total decay probability. We can think of the field phi as living on the contour, which is simply the sum of the two contours. Let's call it C. And here are the boundary conditions for the field. In fact, this is a standard expression for the transition amplitude or probability in the informally. The next step is to evaluate this expression. And since we have the small coupling constant, we can do this in the saddle point approximation. So the integral is saturated on a certain field configuration called bounce, which satisfies certain boundary conditions. So let's discuss its properties. Yeah, and I forgot to mention that since in our case we have mixed states, so all these vacuum states associated with black holes, they are mixed states from the point of view of an outside observer. We should replace here the initial state by its density matrix, the initial state density matrix. So let's discuss properties of the bounce. The bounce is a solution of the classical equation of motion, which is written here. It lives on this contour C, and I will explain what these lines mean in a moment. Assuming that it is unique, we find that its values on upper and lower parts of the contours are complex conjugates, so here it is real. And from this point, it can be continued to the real time, where it describes the actual evolution of the field after tunneling. And these lines are singularities of this classical solution. Now, the most important property of the bounce is that it must linearize in these limits, t going to t initial, up and low, because it must approach the false vacuum state. But it must approach not just any false vacuum state, but the correct one, the one that we choose, Bulvar, Hartley-Hawking, or Unruh. So how to impose what boundary conditions correspond to a given vacuum state? This is the most important question. And it turns out that these boundary conditions are the same as for the time-ordered Green's function, computed in the corresponding vacuum. So this is just the definition of this function, and it satisfies this equation. So the condition is imposed on coefficients of positive and negative frequency modes in the expansion of the solution in the linearized limit. And these conditions are the same as for the Green's function. To understand it better, let's write again this equation of motion for the bounce, and let's rewrite this equation in the integral form. So here we see that if we substitute different Green's functions here, we obtain different conditions for the field phi. And our statement about the boundary conditions is that to obtain the correct boundary conditions, to make the solution really the bounce, the tunneling solution, describing tunneling from Boulevard, Hartley-Hawking, or Unruh vacua, one should substitute here the corresponding Green's function, the time-modeled Green's function, in one of the three vacuum states. Finally, the decay rate is evaluated as follows. So B here is simply the action of the theory taken on the bounce configuration up to some boundary terms. The general story ends here. And the next question is, can we actually proceed further and make real computation now that we have a method? Well, let's see. In general, if you look again at this integral equation, it is quite hard to solve. Perhaps even harder than the original differential equation, and it requires some numerical procedure. However, one can think of the following bypass. Imagine that you have a model in which the bounce has the following structure. So it has a tiny nonlinear core where it probes the true vacuum region, and it has a broad linear tail of the size of the Compton wavelengths. The crucial observation is that if you look at the core from far away, we don't see its structure. We see it as a point light object, which means that in this region, we can replace the nonlinear term in this expression simply by the delta function. And then we obtain that the bounce is simply proportional to the Green's function. So the method, the procedure is the following. We can look for the bounce solution separately in the two regions. In the inner region, where we can neglect the mass term, since nonlinearities are important, and in the outer region, where we can neglect the nonlinear term. And then hopefully there will also be some overlap region where both approximations are applicable, and we can match the two pieces of the solution, and we can recover the full bounce solution. To implement this procedure, we considered the following toy model. So we took the following potential for the scalar field, and we put the system into the background of a dilaton black hole, which has the following expression for the conformal factor. So this hierarchy between the parameters of the potential ensures the existence of the overlap region. The advantage of this model is that we can actually find all tunneling solutions analytically. Because if we neglect the mass term here, then this part of the potential gives rise to the Liouville equation, which admits general solution. And if we neglect nonlinearity, then we can actually compute analytically all Green's functions in this background, both in the near horizon region and in the asymptotically flat region. And we can do this for all three vacuum states. And again, this is a schematic picture of the potential. Let's discuss our results. First of all, we could check that for the Boulevard and Hartley-Hawking vacuum states, our method reproduces the known prescriptions of how to look for the bounce. While for the Unruh vacuum state, our method allowed us actually to compute the bounce. The results are in agreement with expectations. So the suppressions of vacuum decay are ordered in this way. So the suppression is maximal for the Boulevard vacuum, it is in the middle for the Unruh vacuum, and it is the lowest for the Hartley-Hawking state. Next, in cases when the tunneling solution exists, both in the near horizon region and in the asymptotically flat region, the suppressions are always ordered in this way. So the tunneling probability is lower near horizon than far from the horizon. So there is effect from, this is effect from curved space-time geometry. So, and this is effect from basically quantum fluctuations, from excitations. And this is our sanity checks. It is important to note here that from these two expressions, we see that indeed the catalyzing effect is both due to geometry and due to vacuum excitations of the field. And both effects are equally important. They are the same order of magnitude. We cannot really separate one from another. This is a picture of how this vacuum decay suppressions look like as functions of temperature. And the most important message here is that when we consider the high temperature limit, we see that although the difference between the Hartley-Hawking and Unruh suppressions is parametric, it is enhanced by the inverse of the small coupling constant. Nevertheless, we see that at high temperatures, the suppression of the Unruh vacuum decay goes to 0, same as for the Hartley-Hawking case. In fact, we think that this result is an artifact of our two-dimensional model, and we don't expect it to hold in more general or a more realistic four-dimensional setup. So with this, let me come to the outlook. How are our results generalized to 4 dimensions? Well, our model captures many essential features of, say, the realistic Schwarzschild black hole in 4 dimensions, but not all of them. So 2 things need to be taken into account. The first is the gray body factors. In our model, the effective potential for modes is essentially temperature independent. While in the realistic case, there is a thermal barrier, which is proportional to the black hole temperature, and which changes significantly the flux of radiation to the right side on the barrier. And the second thing is the area growth, area factor. So because of area growth, it causes spreading of the particle flux. While again, in our model, the flux propagates in one direction, doesn't spread. So both these effects are expected to further reduce the Unruh vacuum decay rate. And in principle, our method allows us to take into account both of them. So this is work in progress. Finally, there are many open questions here, which are extremely interesting to study. So for example, at some point, it would be important to compute also the pre-exponential factor in this formula for the decay rate to set the overall scale. It would also be important to take into account thermal corrections to the tunneling potential, which may be important in systems with many degrees of freedom, such as a standard model. And finally, perhaps the most ambitious goal is to take into account dynamical gravity, to switch on back reaction of vacuum decay on gravity, to allow for the gravitational background itself to interpolate. Presumably, this would give us new insights into semi-classical gravity and non-perturbative gravity, since all the standard solutions, they are by construction non-perturbative, and maybe we could get some new glimpse into other related topics, such as black hole entropy or information paradox. Okay, let me stop here. Thank you for your attention.
Thank you very much. Are there any questions? Okay, then I ask question. You said that when lambda goes to 0, when lambda 2 goes to infinity, this goes to 0 for BU. This is an artifact of 2 dimensions. What is not, you think, an artifact of 2 dimensions? What is real?
So this is the ordering. So this ordering is real. So that's the most general result. That the suppression is always smaller. The suppression is smaller for the Hartley-Hawking state than for the Unruh state, and for the Unruh state than for the Boulevard state. And our main result is that we actually managed to compute. We actually managed to confirm this expectation, to make a real computation in some model. And this result we of course expect to be very general, because that's the most underlying physics. And also the fact that the suppression of the Hartley-Hawking vacuum goes to 0 at high temperature limit, this is also very general, because it's like the tunneling in thermal bath, right? And if you increase the temperature, then of course the transition becomes less and less suppressed until eventually it simply goes to 0, and you have classical jumps over the barrier simply because of classical stochastic fluctuations of the field. So this red line is also very general. About this blue line, I'm not sure. So in our model, we found that it is almost the same as in flat space. So there is virtually no catalyzing effect from the black hole. Again, this is not general. We expect that there will be some catalyzing effect in the general case, but not as strong as for the Unruh and Hartley-Hawking states.
Thank you very much. Ask more questions. Okay, then we go to the last talk.
Okay, thank you.
Thank you very much of our session, Paola Meda, evaporation of two-dimensional dynamic black holes sourced by the quantum trace anomaly, University of Genoa.
Genova, yeah.
Genoa, yeah, Genoa.
Yeah.
Yeah.
Thank you. Thank you. So first of all, I want to thank Andrei and all the organization for this very nice meeting and for giving me the chance to present my work. And this talk is fully based on a paper you can find on the archive, and it is a joint work with other collaborators in Genoa. They are Nicola Pinamonti, Simone Roncallo, and Nino Zanghi. In particular, Nicola Pinamonti and Nino Zanghi are my supervisors. And okay, and it is about the evaporation of dynamical black holes in 4 dimensions when the trace anomaly of a quantum field is involved. And okay, so the main framework of this talk, in general, of my work is the quantum field theory on curved spacetime, in which we study the back reaction of the quantum matter field propagating over a classical curved spacetime. And in this case, the dynamical equation which governs this interplay between matter and gravity is the semi-classical Einstein equation, in which you equate the classical Einstein tensor with the expectation value of the quantum stress energy tensor related to this matter field. And this expectation value must be taken on a certain physical state, so omega, let's say. It must be renormalized, so there are very different point splitting procedure or renormalization procedure to obtain this value. But if you do that and if you are able to solve this equation, then you can obtain a semi-classical spacetime, let's say, as a solution, and which encodes the back reaction of your matter field. And this equation has several different applications. For instance, you can apply this equation in cosmology in order to study the early stages of the universe, for instance, taking into account as matter field the inflaton. Or alternatively, you can also apply this equation in the context of black holes. And in particular, probably the most famous result about quantum field theory on black holes was due to Hawking, who proved that when you do not consider the back reaction of the matter field, then you can see that a Schwarzschild black hole emits thermal radiation at infinity, and this radiation is at a temperature pH, that is the so-called Hawking temperature, that is proportional to the inverse of the mass of your black hole. It is a very small value, actually, mostly for astrophysical black holes, but in principle it can be detected in experiments. And okay, and then in our case, we focus our attention on dynamical black holes that are a class of black holes which is different from the static one, because in this case you haven't a global time-like Killing vector field, and that's a notion of time, let's say. So in this case, the computation is more difficult than the static case, and in particular, in general, the process of evaporation, which consists on saying that the black hole loses mass during the emission of this thermal radiation, then this emission of radiation is in general distinct from the process of evaporation, namely from the process of losing mass from the black hole. And in this case, for dynamical black holes, the evaporation of your black hole is strictly related to the dynamics of your horizon. And in the semi-classical picture, using the semi-classical Einstein equation, we want to study the evolution of the horizon, and thence we want to study the evolution of your mass, of the mass of the black hole, using a semi-classical model of evaporation, which can furnish some nice results about the evolution of your horizon. Okay, from a general point of view, for dynamical black holes, we focus our attention on the spherical symmetric spacetimes, which was metric, let's say, is always given by the following line element. In this case, the line element, sorry, is a sum of a two-dimensional normal line element, the gamma squared, plus the standard two-sphere metric. And in the normal metric can be parameterized in different ways. A first choice is to parameterize the metric in terms of outgoing and ingoing light rays, let's say in a sort of classical coordinates for dynamical black holes. And in this case, the V coordinate parameterizes the outgoing light rays, whereas the U coordinate parameterizes the ingoing light rays. Alternatively, you can also use the so-called advanced entity-Finkelstein coordinates, and you can parameterize the normal metric in terms of the Bardeen-Valla metric, in which you can see that in this case you can explicitly find the mass of your black hole, that in this case for dynamical black holes it isn't a constant, but it is a function of V and R. In particular, these coordinates, these advanced coordinates, are the radial coordinates, and V is a time coordinate, and in particular it is useful to describe the evaporation of your black hole, because you can compute the rate of your mass, or the variation of your mass, in terms of this coordinate V. Of course, the main feature of your black hole, of your spherically symmetric black hole, is the horizon. That in this case is an apparent horizon. That is a sort of local definition of your horizon, in which is different from the notion of event horizon you usually find in the static case for a Schwarzschild black hole, for instance. And this definition is taken into account by considering a congruence of ingoing and outgoing geodesics. So in general relativity, you can describe the evolution of the congruence of geodesics in terms of its expansion parameter. For instance, in case of outgoing geodesic, you can use the theta plus function that in some sense it describes the variation of the transversal area of your geodesic congruence. And the idea is to define the apparent horizon H for dynamical black holes in terms of these expansion parameters. And the point is that you want that your horizon to be a surface from which light rays cannot escape. And this property, this fundamental property of your horizon, can be translated into the requirement that theta plus vanishes on H. You have other two further conditions on H. If you impose these conditions, you see that your surface is a dynamical horizon. In particular, it is a future outer trapping horizon. And if you compute these three conditions on this class of spacetimes, you see that the apparent horizon, this horizon, is located on the surface that is exactly the same surface where you find the event horizon in the Schwarzschild case. So in some sense, this definition of horizon generalizes the notion of event horizon in the static case. Moreover, as in the stationary case, you can formulate thermodynamics of dynamical black holes. Namely, you can see the black hole laws in the dynamical cases, from a thermodynamical point of view, as in the stationary case. It was made by Hayward some years ago. Unfortunately, I have no time to discuss in details this topic because it requires some technical tools like the Kodama vector field, the surface gravity. So there is no time, but if someone is interested in this topic, I have prepared an auxiliary slide containing some remarks about this topic. So we are interested in describing the evaporation of a black hole, and the main feature of evaporation of black hole is the negative ingoing flux you can find on your horizon. We can say that always you have a negative ingoing flux on your horizon. Then you can from the semi-classical Einstein equation you can show that the mass of your black hole has a negative rate of evaporation. Namely, if you define the mass of your black hole, that is the mass computing on the horizon, then you can compute from the Einstein equation, from the semi-classical Einstein equation, you can compute the rate, and this rate on the horizon is proportional to this ingoing flux, this VV component of the stress energy tensor. And if you find that this component is negative, then you find that this rate of evaporation is negative, and thus you can say that the black hole is losing mass. The point is that you need the quantum effects to obtain this result, because this component violates the classical null energy condition. So in some sense, in order to obtain this negative ingoing flux, you have to require that you have quantum matter field in your system. And this is the point. We want to show that if you consider, in particular, a massless conformally coupled field, and in particular you consider the trace anomaly arising from this field, then you can show that this trace anomaly can induce evaporation of your black hole. And this is the main topic of our work. In particular, so we consider, in order to obtain this result, we consider a massless conformally coupled scalar field. That is the simpler case, let's say, and we consider the trace anomaly of your stress energy tensor. It is important to say that in case of massless conformally coupled fields, the trace anomaly does not depend on the choice of the state. So that only in this case, the trace anomaly is purely fixed by the geometry of your spacetime. So you don't need the knowledge of omega to compute this guy. The important point is also that in general, if you want to describe evaporation, you need this component, this VV components of T. However, in 4 dimensions, it is difficult to compute this component because in 4 dimensions, in general, there isn't a good notion of state when computing the stress energy tensor. So in general, it is a difficult task to obtain this component and this expectation value in particular. However, we can, instead of computing directly this component, we can relate this component, this VV component of T, to the matter content that is outside the horizon. So instead of focusing our attention on the horizon, we study the matter content that we can find outside the horizon. In particular, we consider this diagram that is a sort of conformal diagram of your spacetime. We consider a portion of our horizon, and we fix an initial data which represents, in some sense, the starting point of the collapse, let's say, and we can show that if we impose some vacuum-like matter condition on your state, on your system. In particular, you impose that the stress energy tensor vanishes on these 2 lines that connects the initial condition, the initial point of your system. Then we can show that under these statements, under this hypothesis, let's say, the variation of the mass of your black hole along this portion of the horizon is equal to this right-hand side. And up to a minus sign, it is equal to a quantum source term, let's say. In this S term, there is the trace anomaly. So in some sense, on the right-hand side, you can find the trace anomaly of your matter field that is contained inside the domain D. Moreover, you have also an energy flux component, let's say, an energy flux term that is evaluated on this hypersurface gamma. And this energy flux depends on the UV component of T. So we can say that the mass is balanced by these two terms. And in particular, if one can prove that the trace anomaly can force the mass, the variation of the mass, to be negative on the horizon, then we can conclude that the evaporation is occurring because of the presence of the trace anomaly in your system. And the point is that you can obtain such a result if you add another condition of your system. Namely, you impose on your system the following average energy condition that is imposed, let's say, on the W term inside this equation. This is a very technical, condition, so I don't want to discuss in details this condition, but in general, let's say it is a sort of average condition that involves quantum expectation values, let's say, and it holds for a carefully chosen exponential smooth function f. But the point, the main result is that if you impose this vacuum-like matter state in the past of your horizon, if you impose that such average energy condition holds on your system and it fixes in some sense the sign of W, and moreover you assume that there is a trace anomaly in your domain, then you can prove that this variation of the mass is negative on the horizon. And thence there is evaporation in your system. So it is we decided to test our result in some physical examples, let's say, and we have made an approximation. Namely, we have assumed that in a certain level of approximation, the background geometry that you can find outside the horizon can be quite similar to the one obtained in a classical model of gravitational collapse. Since it is difficult to compute in general the back reaction, in general to compute the semi-classical spacetime.
Oh, we have 3 minutes.
Oh, thanks. So I have finished. Thank you very much. We have assumed that the semi-classical Einstein equation can be fulfilled by classical geometries, and we have found that if you consider a Schwarzschild spacetime, then you can find that the Schwarzschild spacetime is not a solution of your semi-classical Einstein equations because the mass is constant, and actually the rate of variation vanishes because m is a number. Instead, if you consider the Vaidya spacetime, which describes a null radiating star, and the mass in this case is a function of the advanced time b, then you can explicitly compute the negative flux on the horizon. You can, it is proportional to the lambda coefficient that is in front of your trace anomaly, and then so you can compute both the rate of variation and the variation and the rate of variation of your entropy, where the entropy is defined as proportional to the area of your horizon. So I have no time to discuss other details about this topic, but of course, if you have questions, please go on or please contact me. Now, at the moment, I have finished. So thank you very much for your attention.
Thank you. Please ask questions. Yeah. Maximilian.
Sorry, I was just clapping. Thank you for a very nice talk.
Thank you, Maximilian. Thank you very much.
Thank you very much.
Okay. Do you need more time to discuss
as you wish. My auxiliary slide is not so important for the talk, but if you are interested in seeing it, of course, why not, as you want.
Yeah, I can make breakout rooms and wait 15 minutes. You can discuss all together something what is interesting for you.
Yeah, of course. Okay.
Thank you very much for your talk. And
thank you too.
Open all the rooms. Okay.
Sorry, where can I find the room for the breaking room?
This is a good question because I have never used it. So what I did, I opened, and this breaking room symbol is on the bottom of. So you can discuss using
this room, I guess. Yeah, if you prefer. Yeah, there is no problem.
But you can discuss just here.
Yeah.
15 minutes.
The very briefly discussion. Yeah, this is my auxiliary slide. Let's say in dynamical black holes, in general, there isn't a time-like Killing vector field. But the point is that if you are in a spherical symmetric spacetime, you have another interesting and nice field, vector field, that is the Kodama vector field. That in some sense is the curl, the two-dimensional curl of R. And this vector field, has very nice properties. In particular, it is divergenceless, and moreover, it defines covariantly conserved currents whenever you have a stress energy tensor. And so, in our case, we have a quantum stress energy tensor, so we can define a covariantly conserved current associated to our conserved stress energy tensor. And the point is that by means of this equation, you can obtain our equation, let's say. And the point is that you can also compute the surface gravity of your black hole, and this surface gravity is given by the following function. And the main result due to Hayward was that you can using this Kodama vector field and this surface gravity, you can write the first law of black hole thermodynamics for apparent horizons, and then it has the following form, and you can see that more or less it generalizes the standard first law of black hole dynamics in the stationary case, because there is the same. It has the same form of the first law of thermodynamics, let's say, where the energy is the mass, the surface gravity is again the temperature of your black hole, the area is the entropy, and this UV component of T is actually the work done by the matter field. So this is the main result by Hayward, and in particular it generalizes the stationary laws, let's say. It is the result, let's say. Very brief, very briefly comment, let's say.
May I ask a question?
Yes, of course, please.
Yes, nice. It's well, I'm afraid it's maybe more of a tangent, but I was interested in the interpretation of the temperature as the tunneling probability, because I've heard this also mentioned in a talk by Rainer Ferch, and I looked quickly into this, but I got myself confused what the right interpretation is, because if I think of this as a proper horizon, then there is definitely no possibility for, in some sense, a two-way tunneling, which is forbidden by causality. So I wondered what's the right interpretation of this so-called tunneling probabilities, and I wanted to hear your take on these things.
Yeah, thanks for the nice question. Unfortunately, I'm not very expert about this topic because it was written by Nicola Pinamonti, that is my supervisor. So I only have read quite carefully this paper. But the idea of this result by Pinamonti and Vark is that you can see the surface gravity of as a temperature of your black hole, because it arises from a certain scaling property of the Hadamard function, of the Hadamard state. The idea is that when you have a semi-classical picture, when you are in quantum field theory and cross space-time, you need the states to compute two-point functions or expectation values. And the right choice to compute such expectation values is to choose a Hadamard two-point functions. If this Hadamard two-point function exists, then you can compute in principle these expectation values. And the point is that if you make a careful analysis of the property of your Hadamard two-point function on this class of spacetimes in the vicinity of your horizon, you can see in some sense that you can interpret this scaling limit as a sort of tunnel probability across the horizon. But it is indeed, it is an interpretation. So I think, as you have said, it is better to view these properties as a pure a fundamental property of your two-point function instead of the tunnel probability that is quite misleading in my opinion. So there is actually a property of your two-point function that you can obtain in this class of spacetimes, and you can see that this scaling properties is related to the Kodama vector field. Thanks to the Kodama vector field, you can define the surface gravity, and you can see that this surface gravity is directly related to this property of your Hadamard two-point function, let's say. This is a long story short, but I repeat that I'm not an expert about these papers, but if you are curious, if you are interested, we can talk in much more details, maybe with Nicola, that is one of the authors of this paper that you can find here. So.
Very nice, thank you. Yeah,
you're right.
Yeah, I think this tunneling probability, well, it sounds a bit misleading just because it should not be allowed to tunnel.
Yeah, exactly. Yeah, I agree with you. Yeah. It is true in Schwarzschild because you are in a static spacetime, so you have you are a global time like Killing vector field, so it is a better interpretation. In this case, it is quite misleading, I guess. I agree with you.
Thank you very much for your detailed comment.
Yeah,
Thank you.
You're welcome.
So those of you who want to discuss anything can be free. So the session, you're always free. The session is over, but you still can discuss if you want.
Yeah, so again, thanks a lot for these nice talks and to all speakers.
Yeah, thank you.
Thanks, guys. Goodbye. See you tomorrow.
Goodbye. See you tomorrow. Okay. Okay. It's time for dinner in Italy, so maybe.
Yeah. It is.
So thank you very much again, and see you tomorrow. Yeah.
See you.
Bye.
Bye.